Uh, so welcome back, and let's have the second lecture of week 3 on polymers. So what we discussed in the last class is that real chains which have real chains with excluded volume, so they are in a more expanded state. So they are more in a so basically their radius of gyration or the end-to-end distance, they go as n to the power 3 by 5. So they are more swollen, right? So they occupy a larger average size. Their size is more than an ideal Gaussian chain. And that happens because there is overlap between monomers, which costs an energy. And if you remember, we used a quantity called the excluded volume V. And basically, depending upon the amount of overlap, there is more, there's energy cost. And as a consequence of which, in the Fourier theory, we saw that the chain gets swollen. Now, while that's a size, that's a measure of the size of the polymer chain, of course, statistically averaged, and it's an estimate. But the question is, how much is the value of this excluded volume V? And how important are excluded volume contributions? So these are the quantity, these are things which we want to address in today's lecture. So how does one calculate the excluded volume V? And a chain might be swollen in good solvent conditions, but then the question is also that how much is the overlap excluded volume? And there are experiments, scattering experiments, by which you can measure it. So you want to get the microscopic properties of the polymers, and right, and not the chemical details, but amount of excluded volume, using the developing the language that physicists talk while talking about polymer physics. And how do you relate it? So we are basically going to discuss such things today. So the first thing we are going to discuss is how frequently do monomers come in contact using the ideal chain approximation. And that can be given by, so basically we want to say that each contact or overlap of monomers, uh, they cost energy and they cause the polymer chain to spread out, right? And we saw that the an estimate of the size, say Rg, goes as n to the power 3 by 5, where 3 by 5 is the so-called Fourier exponent. Now, suppose you have a flexible chain, the so-called freely jointed chain model, if you like, and a spherical monomer is of size V, say, right? Then one can calculate the overlap volume fraction pi star. And here we are calculating, we are considering only monomers from a single polymer chain. Okay, so we are looking at a dilute system. So we have a polymer coil which is basically uh, distributed in space, and uh, that polymer has size on an average R, and you're looking at monomers of the single polymer chain and how often do they come in contact with each other. All right. So for that, what we calculate is phi star, the overlap volume fraction phi star, and the volume of each monomer of n monomers. So each monomer would have an estimate of 4 pi by 3 b cube, where b is the size of the monomer. So basically, we are dropping all the p factors. 4 pi by 3, those we are dropping. So it's b to the power d, d being the dimension. If it is 3 dimensions, then this is 3. So this is the volume of one monomer, dropping prefactors, into n, the number of monomers, and r to the power d. R is the size of, on an average size of a polymer chain, the entire polymer chain. So if you like, this is an estimate of the pervaded volume. So so that goes as r to the power d. If it is 3 dimensions, r cube. Again, we are dropping prefactors, right? So we are dropping prefactors, and then this goes as now r uh, is b into n to the power half. You are taking an ideal chain approximation here to the power d, And then basically this quantity, if you get on the numerator, you have n, and for 3 dimensions this is n to the power 3 by 2. And so basically the overlap volume fraction phi star goes as 1 by root n. So if you have longer and longer chains, then the basically overlap volume fraction decreases with uh, increase in n. But okay, but even before but, so the probability of a monomer contacting another monomer, getting in contact with another monomer uh, of the chain, on the chain, is proportional to 5 star. So basically it's how much of the what volume fraction of that pervaded volume is occupied by monomer. So the probability of a monomer contacting getting in touch with another monomer uh, goes as 5 star, which is the fraction of volume filled with monomers, and that goes as 1 by root n. But that's the probability. But number of contacts that you would have within a polymer chain, a single polymer chain with n monomers, is basically n into probability of contact, and that now goes as, I mean, n into 1 by root n, and that goes as root n, and root n is in the numerator, right? So the number of contacts, root n is much larger than n for large n, and then so the number of contacts actually increases per polymer chain as root n, which is the result in 3D, right? And the number of contacts increases for long chains in then 3D, and then the energy of contacts overlap increases as root n in 3D, right? And of course, thereby polymer chain will swell. Now, if you are in 2D, you can repeat the same calculation, except now D will be 2, and then you can see that the energy of contacts, or the number of contacts for long chains in 2D, goes as n. And so the energy for contacts in 2D, if you have a 2D, somehow the polymers were confined to 2D, the energy of contacts is significantly more. The energy goes as n. As a consequence, in 2D, the Flory exponent is not 3 by 5, which is a result for 3D, but for in 2D, it is 3 by 4, actually, right? So it swells even more in 2D because the energy of contact between monomers of a single polymer chain, because of finite excluded volume, is even more for 2D. The effects are much more, so it swells more. So that's the result. Okay. Now, in this, what we were trying to show is basically it is important in 3D and 2D to incorporate the energy of contacts, due to which a polymer would significantly swell. Now, that depends basically also on the excluded volume, right? So the excluded volume of the monomers. And now what we are trying to do is get an estimate of the excluded volume of monomers. For that, uh, we will define the so-called Mayer's function. Okay, and Mayer's function is basically denoted by f of r, and that is basically exponential minus u of r, where u of r is the interaction potential between monomers. It decides whether it's repulsive, whether it's attractive, whatever is the nature of interaction between monomers, that's given by u of r, monomer interaction potential, by kbt minus 1. Okay. And why it is defined so, what is the physical motivation of it? Of course, we'll discuss it, but we'll do a bit of maths and then come to the physical picture of it. So this is a mathematical definition. That's the mass function, and the excluded volume is defined as, so the excluded volume is denoted by V minus sign negative of the integral of the mass function integral over all of space, right? Now the question is, so depending upon what the microscopic interaction between the monomers are, you will have different values of excluded volume. Now, suppose that, of course, you have a polymer dispersed in a fluid, but the polymers have, the monomers, of course, they are taking different conformations, but if two monomers come close to each other, then there are dispersion like forces, attractive forces between the monomers. And at very short distances, of course, monomers can't overlap, because there would be extremely strong repulsion between the electron clouds, say. So there is a very strong repulsion at very short distances, at distances say less than sigma, which is the size of the monomers, if you like, right? But at just beyond sigma, so sigma is the diameter of a particle, right? So if this were two monomers in contact, and of course there's a chain like this, and two, so after, at the end of it, two monomers have come in contact, so the radius would be sigma by 2, and the center to center distance would be sigma, which is again the diameter of the monomers. You are assuming identical monomers. Then for any distances less than sigma, there is a strong repulsion, and at slightly higher distances greater than sigma, there is some dispersion forces, attraction due to dipole oscillations, and that goes as sigma to, by r to the power 6. Okay, so it goes as 1 by r to the power 6, and it's an attractive force, and this decays very sharply at larger distances. It goes to 0. And a reasonable model to, if there is this dispersion forces and attraction between monomers, is the so-called Lennard-Jones potential, and that looks as that can be written as 4 epsilon. And why? If you write it in this form, like 4 epsilon into sigma by r to the power 12, which is modeling the hardcore repulsion, minus sigma by r to the power 6, which is modeling this attraction. And if you write it in this 4 epsilon form, then the depth of the potential at its minima is epsilon, right? And the potential goes to 0 at r equal to sigma, and so on and so forth. So, so this is a reasonable model for a polymer in a solvent with attraction interactions. And but in some cases, you don't have that attraction. Suppose the monomer has no particular preference between whether a monomer is in contact with the background solvent particles or with other monomers, then you typically model the interaction by a hardcore potential, right? And so hardcore potential is basically you take this repulsive part of the potential and don't take any attraction. So for the hardcore potential, okay, so you basically take this to be infinity if two particles are just overlapping at distances less than sigma. And then the Myers function f of r can be written as e to the power minus infinity minus 1, and Myers function is minus 1 for the hardcore potential, right? So if you wanted to plot f of r versus r, right? So then up till sigma, if you assume the potential to be infinity, the Myers function would be minus 1. But basically, from, if there was an attraction, then you would have basically the Myers function would give such a positive value, right? If you had only hardcore, then you would only have minus 1 up till sigma, and then it becomes 0. On the other hand, if you have an attractive part as well, then you will get this peak, right? So the hardcore is purely repulsive to prevent overlap. Now, before we go on, I understand I've thrown a lot of Myers function and formulas at you, but what's the physical picture? So basically, when a polymer is dispersed in the solvent, where these red particles are the solvent molecules, and this is a schematic diagram of a polymer chain, you can have 3 different cases. Okay, it is possible that it is energetically favorable for monomers to be in touch with each other. So there is a energy Again, I mean, there's a negative energy. So the monomers prefer to be in contact with each other rather than monomer um be in contact with the solvent. And then this weak attraction can be modeled by the Leonard-Jones type of interaction. That's so that's one case. Or the case two could be that monomers have no preference energetically to be in contact with the solvent or with other monomers. The only interaction that you have, that when two monomers come in contact with each other, you have a hardcore repulsive interaction, and that's when you use the hardcore repulsion. And else, the case three could be that the monomer actually wants to be in contact with the solvent. It's energetically favorable for a monomer to be in contact with the solvent, and there's a significantly higher energy cost over and above the hardcore repulsion uh, for two monomers to be in contact, right? So suppose that the two monomers are charged, right? So they, then even at large distances, there would be mutual repulsion between the monomers. So the V of R versus R would be basically this hardcore repulsion, of course, and then there's an extra repulsion, right? So in that case, there's an extra repulsion. The U of R would be infinite at hardcore repulsion at distances less than sigma. But even at distances higher than sigma, there's some extra repulsion which could come due to charge, or it could come due to other reasons, which we are not going into. So suppose there's an effective repulsion between monomers, and it would rather be in contact with the solvent. So in these three different cases, the question we want to discuss is, what is the value of this excluded volume interaction, which, so what is this value of the excluded volume, which is given as the negative integral of the Myers function, right? So basically we'll be discussing f of r, the nature of f of r, and what will be the value of the excluded volume in the three different cases. And if you calculate that, and of course experimentally you can measure that also, then we have an idea about what are the microscopic interactions between the monomers, how much will it swell, and so on and so forth, right? So this is where we are heading. So, so this is the physical picture. Now going back to the discussion of the Myers function. So I said already that Myers function is -1 for the hardcore repulsion case, right? And this adds basically a contribution which corresponds to the minima of Leonard-Jones, right? Now suppose the Leonard, I mean, it's an attractive interaction. So I'm not writing the functional form, but if it's an attractive part, then it would be minus epsilon, right? Or -4 epsilon. And then basically the Myers function in this range, right, would be e to the power minus epsilon. I mean, of course, there will be a R dependence also by kBt. And then you can see that the Myers function will be positive, right? So an attractive interaction will give a positive contribution to the Myers function, whereas repulsive interaction will give a negative contribution to the Myers function. But remember, excluded volume is negative of the integral of the Myers function. Okay, before considering even the Leonard-Jones, I mean the full potential, let's consider. So basically this is the excluded volume. This is the negative of the Myers function. And there is basically a contribution which is coming from the hardcore repulsion, right, which is from 0 to sigma, which is basically integral of this part, right? And the excluded, so there are two contributions to the excluded volume. One is the hardcore repulsion part, and this part from sigma to infinity. So from sigma to infinity is the interaction above the hardcore. So before we discuss the contribution above the hardcore, right, let's discuss what would be the value of the excluded volume. for only the hard core, where you have basically only this and 0 after that. So then the V for hard core would be minus 0 to sigma minus 1, and integral over all space, which you are writing over 4 pi r squared dr, right? And for this, so basically this is from 0 to sigma, and from sigma to infinity, the contribution to the potential is 0, right? If you have only hardcore interaction, so e to the minus 0 by kbt, and so then this becomes 1 minus 1, which is 0. So all that remains is 4 pi by 3 sigma cube, right? And remember, sigma is the diameter of a polymer, of a certain monomer. So basically what it says is, suppose this is a monomer particle, then so then this is sigma by 2 and this is sigma by 2, total is sigma. Basically it says that the excluded volume is 4 pi by 3 sigma cube, which means that no other monomer, the center of any other monomer, cannot come within this distance. So that's why here you have sigma cube and not sigma by 2 cube, right? So it says that the excluded volume is this entire shaded region green, because no other monomer, center of any other monomer, can come within this region. And that is the contribution from to excluded volume from the hard core. Now what does, or how does this excluded volume get modified when you have, say, an attractive potential like Lennard-Jones, or a repulsive potential? So now let's discuss that. So that's the next step. So when the interaction potential includes the negative part of the Lennard-Jones, the attractive part, right? So then what you have is, basically I have basically drawn the same the same figure as previously. So now this part will also start to contribute, where minus function was positive, right? When you, because you're including the hardcore part plus the attractive part, which is contributing positively to the minus function. So then you can basically get VLJ, the V Lennard-Jones, is minus over integral over all space of the minus function, and that can be written as minus 0 to sigma minus 1 d3r, which is the hardcore part. And now this comes with a positive contribution, but remember, this comes also with a negative sign. So this is this negative sign. So whatever is the hardcore part, V dash, suppose is the hardcore part, this part, because minus function is positive and it is going to come when you open the brackets, this minus sign is going to sit here. The excluded volume is going to be, for the Lennard-Jones case, smaller than the excluded volume for the hardcore repulsion case. The hardcore repulsion case, just to remind you, was 4 pi by 3 b cube. But the excluded volume with the Lennard-Jones case is going to be smaller than V dash. Okay. Now, if epsilon, which is the depth of the potential, it increases, then this VLJ will decrease. This excluded volume due to attraction, the VLJ, the total due to the hardcore plus the attractive part, it will decrease. And if you keep on increasing epsilon, there will reach a regime when the excluded volume actually becomes 0, and then it can become even negative. And this is coming, the excluded volume is negative, but remember, there is still an hardcore repulsion, right? So there is a hardcore repulsion, monomers can't overlap, but because there is an attractive part of the potential and that is strong enough, that is essentially negating or cutting off the hardcore contribution, and it can even become negative, right? So VLJ can become negative, so that the effective, so there will be effectively an attraction between monomers, and so the polymers will actually start to shrink rather than spread out, and that is because of strong attraction due to epsilon, the Lennard-Jones, right? The attractive part of the, and it can happen that spread out polymer, which is called a coil configuration, right? And if epsilon becomes too large, then there will be an effective attraction and it can collapse and form even a globule. So this we'll discuss in the next class. But even before that, even before it becomes a globule, let's discuss that at intermediate values, at some values before excluded volume becomes negative, VLJ can even become equal to 0, right? The excluded volume becomes 0, but remember, there is a non-overlap. There is still, so this excluded volume parameter becomes 0 for the Leonard Jones for significantly higher values of the attraction. But remember, there is still a hardcore repulsion because that cannot go away. That is real. We are not considering an ideal chain. Just that this quantity becomes equal to 0. So basically, you need a weak attraction between monomers, and that monomers can't overlap. Under such conditions, the excluded volume due to Lj, as defined by the negative integral of the Myers function, can become equal to 0. So basically, what is happening is because of overlap, the polymer would like to spread out like the fluorine. That's what we discussed. But the attraction is trying to shrink the polymers, and at a certain balance, there can be a value of epsilon where these two effects balance out, and basically the polymer chain starts behaving like an ideal polymer chain. Okay. Okay, so rather than talk about changing epsilon in experiments, it's often easier to change the temperature. So just let's look at the same problem in a slightly different way, whereas where we write FR equal to basically minus UR, so minus UR by KBT. So here now I'm writing down the explicit form of U of R, which is the Leonard-Jones potential, right? 4 epsilon by KBT and so on and so forth. And so basically what will happen, suppose you have the same polymer chain, so epsilon is remaining fixed, but you are changing temperature, and T2 is smaller than T1, so that 4 epsilon by KB T2, yeah, is basically greater than 4 epsilon by KB T1. Then basically what will happen is that the Meyer function will have a higher height, and of course if you're integrating over basically this curve, and the more you decrease temperature, right, the height of this is going to increase, and it can increase to such a value that this integral over the hardcore repulsion and this integral of this curve at r greater than sigma exactly cancel each other out, and at a particular temperature called the theta temperature, it's the temperature at which VLJ, or the excluded volume, becomes equal to 0, and the chain starts to behave like an ideal polymer chain, right? Remember, so this remains unchanged. So I mean, independent of temperature, two monomers cannot sit on top of each other because that will be a very strong repulsion from the electron crowd of the two monomers, right? But as you change temperature, because this factor is changing, as a consequence, the Myers function keeps on increasing, and you can reach such a temperature so that the integral from this hardcore repulsion and the integral over this contribution is opposite in each other in sign. They cancel each other out, and the temperature where they exactly cancel each other so that the polymer starts behaving like an ideal chain is called the theta temperature. Okay, and just above the theta temperature, or temperatures above the theta temperature, the excluded volume actually behaves like, can be written as I shall show just here, can be written as 1 minus theta by T d cube. Okay, so basically, and this is valid for temperatures above the theta temperature. So when T is greater than theta, of course, there's a finite volume, there's a positive excluded volume. But as T slowly approaches the theta temperature, so at T exactly equal to theta temperature, this quantity again becomes 1, so that the excluded volume becomes equal to 0. And that's exactly what I told you, right? But this is the basically this is the temperature dependence of the excluded volume at temperatures above the theta temperature. Okay. So this is what I have written. And how do you get this relationship? So basically what you are doing is f of r is e to the power u by kbt minus 1. And if kbt is high enough, right? So if 4 epsilon by kbt is much less than 1, then you can expand this exponential so that you can write it as 1 plus x, so 1 plus u of r by kbt minus 1, and we are ignoring higher order terms. And then if you do this integral, so basically v, the excluded volume, remember this holds only when this condition is satisfied. So when you can ignore higher order terms, and then what you're doing is basically writing down the Myers function in terms of, if you like, the hardcore repulsion part and the other part, right, from sigma to infinity, from 0 to sigma and sigma to infinity. And then if you just do this integral, this will be 4 pi b cubed by 3. Now cancel pi and 3. And the rest of the term will be 4 pi doing an angular integral by kbt ur r square dr, right? And if you take 4b cube out, right, there are two terms, so you have just taken 4b cube out, then you have written 1 minus pi by b cube by kbt, because you're taking b cube out, you have an extra b cube here, and what you get is such a term. And then you can write 4b cube 1 minus theta by t, right, because there's a kbt here, where theta temperature can be calculated as pi by b cube kb integral 0 to infinity u of r squared dr. So whatever is there, you call that the theta temperature, and you have a t dependence here, right, which is basically got by expanding exponential when this condition holds, right? So you also know, and this actually works out pretty well experimentally, but this t has to be greater than the theta temperature, of course, right? So what is the message? So the message is polymers have nearly ideal conformations at theta temperature, and just example is polystyrene. Now don't ask me the chemical formula of polystyrene, but I'm sure you can look it up if just Google. So I'm just giving a real example that this is not just a theorist's construct, but it's real. And polystyrene in cyclohexane at 34.5 degrees centigrade, it basically behaves like a polymer in a theta temperature solvent, right? So polymer solvent pair at theta temperature. This I took from the book of Rubinstein and Colby. Okay, and at theta temperature we equal to 0, in spite that there can't be overlap between the monomers, right? Because there's an attraction. But now, if you keep on increasing the attraction, you can go into the poor solvent case, right? Because of epsilon, the depth of the attraction, the depth of the potential increases. V can become negative after 0. And when B cube is less than V is less than 0, then you call it a poor solvent. And ethanol is a poor solvent for polystyrene, so you have a negative excluded volume if you are considering polystyrene in a ethanol solvent. And you can also have the non-solvent, where the excluded volume goes as minus bq, right? uh, and this is negative, so we have negative excluded volume. Just as a reference, For the hardcore repulsion case, when you had pure repulsion, no attraction, then the excluded volume was 4 pi b cube, cancelling pi, and which basically you are dropping off this free factor, you can write it as b cube. And for a non-solvent, this excluded volume is negative b cube. Right? So you classify how the polymer is behaving depending upon the monomer or the polymer solvent interaction. And when it's a good solvent, then basically it spreads out, right? Okay. And by the way, when you have pure hardcore repulsion, then the system is also called athermal, right? Because basically then whether you have and suppose there's no attraction, the monomer has no preference whether it's in contact with another monomer or in contact with another solvent molecule, and you have to consider only hardcore repulsion, then it really doesn't matter what temperature you put, because temperature plays practically no role, and you always have a very swollen configuration, right? Thermal polymers are always swollen. A polymer at a theta, a normal polymer would be swollen at very high temperatures, but as you lower the temperature, even if there's slight attraction, you will reach a temperature where it will start behaving like an ideal chain, is not swollen anymore, and at even lower temperatures, the attraction will take over and the spread out swollen polymer coil will collapse into a polymer globule. So when it is collapsed, that state is called the polymer globule, right? And yeah, so that's what will also happen in a non-solvent or a poor solvent, essentially. Okay, so with that, let's go a few steps ahead. Now, I've been talking about really a flexible polymer chain, but as we discussed, often polymer chains, physicists at least like to talk about, they love flexible polymer chains, and this property becomes valid when if you scale up the monomers, so that you describe the polymer chain as a flexible chain of Kuhn segment, right? And if you remember, the Kuhn length was double the persistence length, which I worked out in terms of the worm-like chain model a few lectures ahead. So if you're confused, just look up what is Kuhn segment and then come back here. So suppose you have a lot of monomers and there's a finite persistence length. So basically, subsequent monomers are pointing, there is angular correlations between subsequent monomers along the chain. And suppose you can describe some Kuhn length, which is B. And these are the real monomers which are sitting along the chain, right? When you are looking at length scales above the Kuhn length, you can consider this to be a flexible chain. And these are again monomers sitting along the polymer chain. Now we are just considering them to be basically rods of polymers and of Kuhn segment length B, whereas the diameter of the polymer chain gives the width, and that is denoted by D. Okay, now just to give you an idea, that typical polymers have D equal to around 5 to 8 angstroms. So basically polythene has width of around 5 angstroms and polystyrene has the width of 8 angstrom, right? And basically how much the width would depend upon the size of the side groups. And for many polymers, or most polymers, the Kuhn length is 2 to 4 times D. And of course, if you have longer persistence length, if you have larger correlations between bond vectors along the length of the chain, then this Kuhn length can go up to 5-10 times D, right? So as shown in this figure schematically. And for DNA, or naked DNA without proteins, the D is actually 2 nanometers and B the Kuhn length is actually 100 nanometers because the persistence length can be measured to be around 50 nanometers. So in that case, B by D is as large as 50, whereas usually it varies from 2 to 4 times D, but you can have extremely long Kuhn lengths, right? So that's the message. Now, if you want to describe your polymer physics, not in terms, I mean, of course, you want to describe it in terms of flexible chains and have this language which we are developing. And of course, polymer physics use this language, the experimentalists. So I wouldn't be interested if somebody tells me, I have polystyrene, this, and I'm seeing this property. I'll say, what is the cool length of the system? What is the persistence length? How much is the excluded volume? Is it in good solvent or bad solvent? And that's how we would talk, right? Because I want to talk in the polymer physics language, of course. And by the way, soft matter is an area where theorists and experimentalists really work with each other, right? So when I write theoretical papers, I convert all the units in such a language so that it becomes easy for the experimentalists to read it. And if you see my last few papers, I mean, so I have actually papers with experimentalists, and the next two are also going to be in collaboration. So we need a common language where I don't have to worry about uh, whether it's, I don't know, polythene or whatever. So this is the language that people talk in, at least polymer physicists talk in, right? So if somebody has made particular polymer, he has to convert it into this polymer physics language. And the question is that suppose you want to talk about a polymer chain, flexible polymer chain in terms of the Kuhn segment, then how would you estimate the excluded volume? Okay, so this is the next question that we are going to address today. To discuss this, so let's set the convention. Suppose there are n actual monomers. So what do you mean by actual monomers? So these blue circles are the actual monomers, and suppose whatever 7 or 8 of them make up the Kuhn length B, right? So suppose you have n actual monomers of the chain, and each of those monomers have volume order of d cube, again dropping prefactors, d being the diameter of each monomer and an estimate of the diameter for each monomer, right? And that polymer chain can be thought to be have n Kuhn monomers, right? So Kuhn monomers is considered as the largest segment of the polymer chain. And the question we are asking is, what is the excluded volume when we describe the polymer chain in terms of Kuhn segments? So what is the excluded volume of interaction of the Kuhn monomers? So this is the question that we are asking, right? So there are capital N Kuhn monomers and N actual monomers of volume Vs, which is equal to d cube. Now, you know that N into D, right? N is the total number of monomers. So basically, so this 7 plus this 7 plus this 7 plus and so on and so forth. So N into D will be N into B, where B is the Kuhn length, right? So there are N Kuhn segments. And then the number of Kuhn segments can be written as ND by B. Now, the energy of contact per monomer pair, the real monomer of the blue monomer pair, is order of kBt, because if two monomers, so they have thermal energy, they have kinetic energy, order of kBt, equipartition theorem, because the system is in equilibrium. And if they come in contact, they can remain in contact only if this kinetic energy is basically converted to potential energy, and then they will repel each other. So the energy of contact per monomer pair is order of kBt, right? But the energy of total number of contacts per chain, as we discussed earlier, should be equal to kBt into Vs, where Vs is the excluded volume of each monomer, right, equal to d cube if you have hardcore repulsion, into n square, right? Because probability and then into n, as we discussed in the Flory theory as well as in the beginning of today's class. And this energy, so this is the energy of interaction due to contact between all real monomer pairs. And just because you are changing the description, right, rather talking about real monomers in a polymer chain, you want to discuss the physics and want to discuss in terms of Kuhn segments, the energy of contact. So you have a polymer chain and there is a certain energy of contact. Now, whether you want to describe it in terms of uh, real monomers of the polymer chain or in terms of Kuhn segments, the energy of total number of contacts cannot change, right? So kBt into Vs into n square should be equal to the energy of contact if the monomers are replaced by Kuhn segments. Right? It cannot depend, I mean, for convenience or to do the physics, well, you want to describe it in Kuhn segments, but the energy cannot change. You have a real polymer in a solution, and the energy of contact is what it is. And it cannot depend upon description, the way you choose to describe the polymer, right? So as a consequence, kBt into Vs into n square, which is the energy of contact of real monomers, will be equal to kBt into the excluded volume. You have Vs here, excluded volume, and this is what we are after. We don't know what its value is, into n square, where n is the number of Kuhn monomers. Right? Is the number of n Kuhn monomers. Right? And this is what we are after. We don't know what is the value of Vk. So to do that, what we do in these two energy scales have, these two values of energy have to be equal. So kBt cancels, and Vs n square, right, equal to Vk, and this is what we are after. And n was, if you remember, was nd by b. It's a definition of how number of Kuhn segments, how many Kuhn segments are there. This is how we calculate it. So this n square is replaced by nd by b, right? And if you have a pure hardcore repulsion, then Vs is written as d cube, and then you have this algebraic equation, Vk becomes equal to b squared d, right? And this is the value of the excluded volume for Kuhn monomers for the hardcore potential. Now note, this is something interesting. So the excluded volume dropping prefactors comes out to be b squared d. If you had taken just the volume of all the monomers, right? So this would be d square, right? So so this would be more like d square b, which would be the basically volume of this cylinder. So pi r square into length. So that would have been d square b, pi d square b. But instead, what you are getting is that the excluded volume for the Kuhn segment is b square into d, which is significantly higher, right? So it's basically a much higher volume than what you would get if you just considered it to be the volume of the cylinder. Now, if you had Lennard-Jones interaction, then of course you can't replace Vs by d cube. But this relation would still hold, and from that you can calculate what is the volume of the Kuhn segment, and you then will replace this V by the excluded volume with a Lennard-Jones interaction instead of a hardcore potential. Okay. Now, just to get ahead, you remember that for poor solvent, when you had spherical monomers, we considered the poor solvent case to be b cube is less than Vk is less than 0. But now, if you're describing in terms of Kuhn segments, you would say that this is equal to b squared d, which is less than Vk, which is less than 0. And for non-solvent, Vk, the negative, would be b squared d. So this was, there it was b cube and minus b cube, and here it is b squared d and minus b squared d for a non-solvent. So compare with basically this slide. Okay, so basically that's what I want to discuss. And just in case, I will just add some other information. It will be basically important for soft matter researchers. This is not exactly part of the course, but just for sake of completion, I would like to say, and this is taken from section 3.4 of the book of Rubinstein and Colby, figure 3.18, that remember that when you have a real polymer chain, excluded volume interactions, so that things can't overlap, then the probability distribution of x, where x is r by basically square root of r square average, for the ideal chain, it was this Gaussian distribution, but for a real chain with excluded volume, a swollen chain, if you have swollen chains, right, and not an ideal chain, but excluded volume parameter is positive, there's a positive energy cost for overlap due to which a polymer chain swells, then basically the p of x would look more like this, right? So basically the end-to-end vector, if you like, there it is swollen, it does not come back to the same point. Okay, so this is what I have to say. This gives at least some introduction of real chains, excluded volume. We have already talked about semi-flexible chains when we discussed the Kuhn segment. If we started out with the ideal chain, but now slowly we are adding corrections and describing a real polymer chain. All of this can be measured by scattering experiments, or even the dynamic light scattering experiments to get an estimate of the size of the polymer chain. If you have a larger n, you can look up the scaling laws and check out what works. Okay, so this is basically lecture which should have been posted last week, and next we will talk about Story-Huggins theory in the next class.